In this lesson, we're going to learn about Euler diagrams. Now, I mentioned Euler diagrams earlier when we were talking about Venn diagrams. Well, Euler diagrams actually preceded Venn diagrams, and Euler was before Venn. But Euler diagrams are much like Venn diagrams, except Euler diagrams we can put objects in more than one place. If you recall, in Venn diagrams we can only put something in one place. So we can use Euler diagrams to describe relationships about all, some, or none. The relationship with the word all will always be one set inside another set. So in this case, if we look at this, we see all cats are animals. So we see the little cats circle inside the animal circle. And this means that cats are a subset of animals. And there it's clear because the cats are inside the circle with the animals. In example number 1, we're going to draw the diagram to show that all birds can fly. So let's see. Well, which is a subset of which? Are birds a subset of flying things, or are flying things a subset of birds? Well, there are things that fly that aren't birds, like bats. But all birds do fly. Well, there's some that don't, but we'll discuss about that issue later. But let's assume that all birds do fly. So we can say that all birds can fly, and birds are a subset of flying things. So that means we could write it like this, where we have flying things, and then birds are the circle inside of flying things, or a subset of flying things. Similarly, for example number 2, we could draw an Euler diagram to show that all squares are rectangles, all rectangles are quadrilaterals, have 4 sides. So, of course, the squares are the most specific, since squares are a subset of rectangles. And rectangles are more specific than quadrilaterals, since rectangles are a special kind of quadrilateral. So all squares are rectangles, so therefore we can write our Euler diagram in such a way that we have squares, which is the most specific type of quadrilateral, which is within rectangles, which is a specific kind of rectangle, and then rectangles, which are a specific kind of quadrilateral. So as mentioned, Euler diagrams can be used to describe relationships about sum. So a relationship with the word sum will always be in one set overlapping another set. So here, for example, we can look at some cats are pets. So what this means that some elements in the intersection between cats and pets. So this is like the intersection, cats, pets, but they're not equal to 0. Or the null set, because, well, yes, indeed, some cats are pets, but yet other cats are not pets, like lions. But then there are pets that are not cats, like, for example, dogs. So it turns out we can have cats, where cats can be lions outside of the intersection, but cats can be pets within the intersection. There are cats that are pets, there are cats that are not pets, and then there are pets that are not cats, like, for example, dogs. In example number 3, How would you use Euler diagrams to represent some animals have 4 legs? Well, some animals have 2 legs like us. So let's look for some animals that have 4 legs, but as you can see, this kitty cat has 4 legs, but the way he or she is dancing, you begin to wonder. But animals intersect things with 4 legs, and of course there are animals that have 4 legs, so we can represent it as things with 4 legs, animals, and then of course there are animals with no legs like snakes, which are animals. And then there are things with 4 legs like tables that are not animals. So animals with 4 legs, well, that would be cats, dogs, and other animals with 4 legs. So Euler diagrams can also represent no or none relationships. And that's a relationship will always be one set separate from another set, and there's no overlap. So, for example, no cats or dogs. There's no such thing as dats, folks. This means that there are no objects in the intersection, nothing here, between cats and dogs. So, the intersection of cats and dogs is the null set, meaning there's nothing here. There's no overlap. So the intersection between cats and dogs is empty. Let's look at example number 4. And how would we use Euler diagrams to represent no fish are purple? And do you think that this statement is true in real life? Well, of course, if you think it's true and that no fish are purple, then the intersection is just the null set. There is no set or intersection set. So the fish intersect purple things is 0 or the empty set. But this is not always true. Just like I mentioned earlier, or I was about to mention about the birds. Yes, ostriches are birds, but to my knowledge, I don't think they fly. Well, it turns out that this is not true either for purple fish. So in the picture here at the right is called a purple parrotfish. So there are fish that are purple. So you would draw it with the intersection. But the issue that comes up here, like for example with the birds or the purple fish, is the idea of bringing in external knowledge. And so this is what happens when we have combining all, some, and none statements for a logical argument. So here we go. How would we represent all cats are furry and some cats are pets in one picture? So we can have 2 different situations. And either of these pictures would be correct, because here we have the first picture shows that some pets are not furry, and the second picture shows that all pets are furry. Without bringing outside knowledge, we don't know which picture is correct, so we should draw both of them, because we don't know whether or not we're going to talk about the purple fish or the purple parrotfish or the ostrich. So again, we have to be careful of outside knowledge. So if we are allowed to bring outside knowledge, we know that there are pets that are not furry, pet fish, for example. We also know that there is the statement all cats are furry isn't actually true either, Because let's see this, for example, the Sphinx is considered a hairless cat. So when we're doing these diagrams, we do not want to bring in outside knowledge unless one is explicitly asked to determine the relationship about things you know about. In example number 5, we're going to draw a picture showing the logical statement, all cats are furry, all furry things are cute, and some cute things are birds. So the first statement is all cats are furry. This means cats go inside furry things. The second statement is all furry things are cute. This means furry things goes inside cute things. So let's see. So we can think of it that way. So now, in example 5, we need to add some statement. So some cute things are birds, which tells us that birds are cute things that must overlap. So here we have birds, we have cute things, we have furry things, we have cats. And here we have the same thing, cats, cute things, furry things, and cats. But birds can be, well, they're cute things, but would we consider birds to be also furry things? I mean, are feathers considered furry? So these are possible diagrams that you can draw for the birds. Now, it's a little bit more straightforward with numbers. So let's look at all numbers. And we saw this briefly earlier when we were talking about the counting or natural numbers. And recall that these numbers are the set 1, 2, 3, 4. And these numbers were all part of the whole numbers. So remember, the natural numbers were inclusive in the whole numbers because the whole numbers we added in the 0 plus the natural numbers. So how would we draw this diagram? Well, let's see. Here we have the natural numbers, 1, 2, 3, 4, to infinity. And then we have the whole numbers where we add in a 0, which makes the set a little bit bigger. So the natural numbers are a subset of the whole numbers, and that would be how we would look at the Euler diagram of that. In example number 7, we're going to ask ourselves a question about certain numbers that we looked at earlier. So we want to ask, where do the square numbers go, the Fibonacci numbers, and the triangular numbers? And it turns out that these are natural numbers. So they would be part or a subset of the natural numbers set. So you can think of them as circles inside the natural numbers or subsets of the natural numbers. Now, in this case, we're going to use our knowledge of sets of numbers to determine which statement is correct. All integers are whole numbers, or all whole numbers are integers. So let's look at the following. Where the rational numbers would go and where the irrational, and would the irrational numbers overlap the rationals or not? And then, of course, where would the natural numbers go? Well, we kind of saw something like this earlier. And it turns out that the irrational numbers do not overlap. But the natural numbers are the most inner, and then if we add 0, we get the whole numbers. And then if we add on the negative numbers, we get the integers. And we saw that earlier. So if we were to look at the real number system, we see, as I just mentioned, the irrational numbers are not within the main diagram here. They're outside of the main diagram because they do not overlap the rational integers, whole numbers, or natural numbers. And recall that these make up the real number system. So we see that the irrational numbers are real numbers, but they are not a subset of any of the other number types. So now we're going to place elements inside the Euler diagrams. And as mentioned, Euler diagrams, you can place an element in more than one place. So suppose we know a cat named Fluffy. And where in the circles for some cats are pets do we place Fluffy? Well, note the whole set is using the circle. So here we have Fluffy. Fluffy can be a pet, cat, but Fluffy can also be a cat that isn't a pet. So, for example, Fluffy can be a lion, and a lion, despite what you may have heard on the Lion King, Fluffy, a lion, is not considered a pet cat. So we can put F here too. So if Fluffy turns out to be a lion cat, well, then Fluffy would be here, but Fluffy could also be a pet cat. So we use F to represent Fluffy. So Fluffy is a cat, so it must go somewhere in the circle of cats, but as mentioned, Fluffy may or may not be a pet cat. So in the Euler diagram, if we're not sure where the object goes, we can place it in all the places where we think it could go. And this is in contrast to Venn diagrams, where we know exactly where each object goes, and we always place each object in only one place. So looking at question number 9, we draw a picture showing the logical statement, all cats are animals, Fluffy is a cat, and Buster is an animal. Well, let's see. How would we describe this in an Euler diagram? Well, here's animals, here's cats. All right, so we know Fluffy is a cat, and that's made very, very clear. And we know we have the animals, and we know cats goes inside animals. But Buster is an animal, but it could turn out that Buster is a cat. So Buster could be the name of a cat, or Buster could be the name of, let's say, a snake. So a snake is an animal, but a snake certainly is not a cat. So now we're going to draw another picture of using Euler diagrams to discuss a logical statement. So no ducks are blue, Fred is a duck, and Cindy is not blue. Well, we see blue things, and we put two separate circles because they do not overlap since ducks are not blue. Fred is a duck, so Fred definitely goes into the duck place. But Cindy is not blue. But Cindy can be a duck, yes, but Cindy can be anything else. Cindy could be a cat, Cindy could be a dog, or Cindy could be a person. Who knows what Cindy is? So we can put Cindy here in the empty space. So a little key to remember or to help you, so to give you hints on how Euler diagrams work. So here's the all statement, here's the sum statement, some A are B, and then here's no A are B. So let's see how we could use our quote-unquote quick key. So suppose Fred is in A. So here's where he would go in each picture. Fred is A, so he's inside, and then he's a subset of a bigger set. If Fred is in A, he can be either in the intersection of A or outside of an A. Like, for example, the pets, the pet cats, and the cats that are not pets. Or Fred can be part of a set A that does not intersect with B. For example, this would be purple things, but Fred is a yellow duck. Now let's suppose Fred is in B. Well, where would he go in each picture? Well, Fred can be, if Fred is an animal, okay, so, well, and Fred is also can be, but we don't know what Fred is in B, and we don't know, so he can be in A or B. Fred, like before, above here, he could be in the intersection, or he can be outside of the intersection. And here, similarly, Fred can be in the set here, but it does not intersect there. So it turns out that he could be in two places because B has two parts to it. So here, this is the reason, let's look more closely at this one, that suppose Fred is in B. Well, we don't know we know that Fred is something in B, and we also know that Fred could be also in A, because there are two parts to this. So Fred could be in either A or B. So we can only figure out if it's more specific, if we're more specific about what Fred is and what we're talking about in that particular diagram. Now lastly, let's suppose Fred is not in B. Where would he go in each picture? Well, Fred is outside of B here. He's not in A, he's not in B, he's outside. Just like when we were talking about the student who didn't like fried or roasted food. So that would be a similar situation here. Similarly here, if Fred is not in B, well, Fred can be outside of A and B, or Fred can be in A. But he wouldn't be in the intersection because then he would have to be part of B. And then, of course, again, here he can be outside of A and B, or he can be inside A. So in the first one, Fred can only be in one place because not B means not in A either. Thank you very much, and stay well, and I hope you found this video useful in understanding a little bit about the Euler diagrams.